Hey, welcome back to Fat Mama Physics. In this video, we're going to talk about radioactive decay, including alpha, beta, and gamma. So looking more specifically at examples. So hopefully before watching this video or trying the examples, you would have known the difference between alpha, beta, gamma decay. You can differentiate the different levels of penetration, what is able to stop it, what is the nature of the charges that are in and the particles that are involved. Hopefully you understand that for a beta minus decay that you're going to get essentially you have a new neutron getting converted into a proton and an electron, as well as an antineutrino in the process. Say with a beta decay, beta positive plus decay is the opposite, in which a proton gets converted to a neutron, and as well as a positron, which is the antiparticle for an electron, and of course at the very end a neutrino as well. So more on those specific particles later in this unit, but essentially you kind of have an idea of what all of these reactions look like. So these examples that I will go over will be on how to predict the products of such a reaction, and that includes the atomic number, the atomic mass, etc. Okay, so starting with an alpha decay here, we want to fill out the missing blanks, and to do this, we actually need a periodic table. You are not expected to memorize the periodic table for any sort of final exam, or actually for a physics final exam at least. So I'm just going to pick a random one from Wikipedia. We just need to know what element we're talking about, okay? So here we have an alpha particle, alpha decay, and it looks like the alpha particle is shown. We just need to find out what the missing nucleus is after the decay. To do these type of questions, essentially the atomic mass has to be conserved, as well as the atomic number has to be conserved. Well, to be more exact, the charge has to be conserved. So we're looking at charge conservation, meaning how many positive charges and negative charges have to be balanced at the end, at an end of a reaction, and here the atomic mass has to be conserved. So to figure out what you're missing, think of it as filling these boxes up. You're going to have to fill the element. We can do that later. But we have to fill in the box up there, and as well as this box down here. The box at the top is the atomic mass, and we know that has to be the same, meaning that 4 plus something here is going to give us 224. And the one number that comes to mind here, that's going to be 220. 220 plus 4 is going to give us 224. So that's the first number that we can deal with. The bottom one could be the second one. So again, since this is the only product for an alpha decay, this 2 plus some other number here is going to give us 88. So the only other number so then essentially you subtract 2 from 88, that gives you 86. And what's going to help you determine the element is, of course, your atomic number. So we go to our periodic table to find 86, which happens to be radon, I believe. Radon, a noble gas radon, so we just put in Rn, and even if you don't know what it's called, you just put in the symbol, so that doesn't affect anything. So there you go. That is that's an alpha decay. And some questions might not even give you this alpha particle here. So you actually have to write the products from scratch. Meaning, since you know it's an alpha decay, you know you have to write this, and then using subtraction, figuring out what is the missing nuclei. Okay, next up we have some examples. We're not going to do in gamma decay because that's very straightforward. It's just essentially you have exactly the same nucleus, but you've released a proton, which is essentially a gamma ray. Okay, so no change to any of the nucleus makeup in terms of protons and neutrons. The examples that we will do here is we're going to do an example of a beta minus decay and as well as a beta plus decay. And notice that none of the products are given, so you will be expected to know what to write on the other side, okay? At this point, you don't necessarily know, you may not know what a neutrino is, you may not know what an antineutrino is, what that really means. You may not know the details of how antimatter works, and that's okay. Essentially, these to do these questions, you kind of have to just memorize the particles that will be produced. We will talk more about the nature of these particles later, okay? So let's start off with a beta minus decay. For beta minus decay, we know for sure that an electron is ejected, and to know that, you just look at beta, whether it's positive or minus. If it's minus, you have an electron that is ejected. So that's gonna look like this, with no atomic mass. Essentially, it's the mass of an electron is very insignificant in comparison to either a proton or neutron, so we just say that is 0. Okay, and then the charge, we're going to write -1. And you're thinking, what? That's usually where we put the atomic number, but for just tracking's sake, it's nicer just to put that there, and it's just how we note that, okay? The other thing we know is produced from a beta minus decay is an antineutrino. So an antineutrino looks like this. It looks like a V, it's got a little E on the bottom, and because it's an antiparticle, more on that later, we put a bar on top to show it's an antiparticle. It also has no charge and no mass, no mass in comparison to a proton or a neutron. So we just put zeros here. So this, in effect, it does not have an effect on the overall calculations that we're going to do, but it is necessary that you put this particle inside your reaction, and marks will be deducted if you don't. So please remember, this particle is part of the reaction. The one last thing that you have to put is essentially the element that you're interested in, that you have to put in here, okay? So this is where we're going to have to do a little bit of math. It's not going to kill you. So first things first, atomic mass is conserved. So all of our particles that are produced here, including your beta particle, beta minus particle, and your antineutrino, have no significant atomic mass. So your element is going to bear the full weight of that 40, okay? And as for the bottom, we have to take an effect of this -1 charge. So think about beta minus decay. It's essentially a neutron gets converted into a proton in an electron. So here's the electron. So in fact, we have to add, we get additional 1 proton out of this mess. And how to show that? Well, we know that this number here plus -1 is going to give us 19. So something plus -1 giving us 19, that has to be 20, okay? So with an atomic number of 20, we go to our periodic table and we locate calcium. So this has to be calcium, okay? Is it stable? That's not our problem to deal with. In fact, okay, we don't know that from this chart. So that's it. That's all you need to do to fill in the missing blanks of a beta minus decay. On to a beta plus decay. And because you know it's a plus, instead of an electron, we know that the antiparticle of an electron, the antimatter of the electron, is going to be a positive charge. We call that a positron. At this point, you're not going to be expected to really understand the difference between a positron and an electron for now, but you just have to remember that all you have to write here is, it looks like an electron, but here on the bottom you just have a +1 charge instead of a minus charge. More on antimatter later. The other particle that is produced is also a neutrino, but this time is not an antineutrino, it's just a regular neutrino, and which it's It's not going to have any charge, and it's not going to have much significant atomic mass. So again, 0, 0, insignificant in your reaction in terms of determining your remaining atomic mass and the atomic number, but of course necessary for the reaction. So that has to be there. The remaining particle here is what you need to determine in terms of the atomic mass and the atomic number. So again, 13 doesn't change because these two are both 0. So 0 plus 0 plus 13 gives us 13, which is correct. However, the bottom plus 1 something plus positive 1 is going to give us 7. So essentially in a beta plus decay, instead of a neutron to a proton, this is a proton to a neutron plus a neutrino. So here we lose a proton and we gain a neutron. So essentially this is going to be 7, taking away 1 proton, that's going to be 6, which is also 6 plus 1 giving us 7. So if you don't know already, atomic number 6 is carbon, but let's say you don't know, you go to the periodic table, you find that the atomic number of 6 gives you carbon. So that is the missing nucleus in this reaction. Okay, so here we go. Here's our examples for figuring out the predicting the products. So it requires you to differentiate alpha, beta, and gamma decay, knowing those specific products. For example, you know an electron comes from a beta minus decay. You know an alpha particle comes out of an alpha decay, etc., as well as your neutrinos, and for you to do the calculation of the remaining nucleus that remains from conservation of mass and conservation of charge. Okay, so there we go. Here is predicting products for radioactive decay. Thank you for watching, and That Mama Physics signing out.